Hey everyone, and welcome to the third lecture on Calculus 1 by yours truly, Raul. This is part of a playlist I plan on making to cover all of Calculus 1, which, by the way, is essentially the same as AP Calculus AB. Before we begin, I strongly encourage you to pause the video whenever I ask a question and attempt to answer it yourself before continuing the video. Let's begin. With this video, I really just want you to understand two things. First off, we can use tables as tools to see function behavior instead of using graphs. Since we can see function behavior, we can inherently also take limits with tables. Second, just like every time we've applied limits before, just because a function is presented in a certain way, in this case through tables, that doesn't really imply that the limit will exist. We have to always check the left side and the right side limits. So as you may already know, we can use tables to describe functions. And you might wonder, well, can we even use tables in calculus? As a matter of fact, yes you can. So let's take a look at this table right here. We can see that it's pretty standard. As x gets bigger and bigger, y gets bigger too. I mean, there aren't any jumps or discontinuities like we talked about last time. So this just looks like a pretty standard linear function. So let's try to apply some calculus to it. Let's start with some one-sided limits. Let's take the limit as x approaches 2 from the left side of f of x. Well, let me talk about why I'm even choosing 2 in the first place. If you look at this table here, there's something about 2 that just makes it the center of everything, and not just because it is at the center of the table. Everything kind of revolves around 2. If you look at this 1.9, it's really close to 2. If you look at the 2.1, it's really close to 2. So it kind of seems like this is where something could go wrong and where we should apply a limit to see what actually happens to the function. So if you remember the loose terminology I've been using to describe a left-sided limit, I've just been saying it's the limit as the x value gets closer and closer to 2 from the left side, right? So left side here will just be this 1.9. So you see, as we get closer and closer to 2, we get closer and closer to 4. I mean, we have 3.9, 3.99. We're just getting closer and closer to 4. So this should just be 4. Now, if we take the limit as x approaches 2 from the right side of f of x, well, pretty simple. Let's think about what that should be. 2.1, 2.01 to 2, and then this just gets closer and closer to 4, it should just be 4, right? I think that's a pretty safe conclusion to make. And so now, if we were to apply the statement we learned last time and get the actual limit value at that x value, well, we see that both of these are equal, and from what we learned last time, that should mean that the limit should, 1, exist, and 2, have that same value. So we should say that the limit is 4. And it might be hard to kind of think about this function just with the table, so let's draw it out graphically. So we see here that we have this plane, and the points that we have on the table are just these that I'm going to very quickly line up. And for the sake of it looking nice, I'm going to use this line tool that I have here. Okay, that's not a perfect sketch, but we can work with it. So if we take a look at this is just a line. It's a continuous function. We've looked at limits on this before. It makes sense that the limit value should just be to this 4 here when we approach 2. So we see if we're coming from the left, it just gets to 2. If we're coming from the right, it just gets to 2. This is just a straight line. It makes sense that the limit is what it is. Now, I arguably think that using tables is a lot better because it just straight up gives you the values of the function. But if you're more a visual thinker, then I think that taking a look at the graph instead of the table might be more beneficial. Okay, so now let's take a look at a function that's a little bit different than before. So as you can see, as x gets bigger, the y also gets bigger. Okay, it's just like before. But now we don't have this 4 that we had before here. We just kind of jump up to 6. So we see as we come in from the left, it gets closer and closer to 4, but then there's a 6. And then as we continue on to the right, it just kind of goes back down to 4. So there's probably a discontinuity happening here. But regardless, let's just apply some calculus and see what happens. So let's take the left-sided limit. So that'll be the limit as x approaches 2 from the left side of f of x. So if we look at the table, as we get closer and closer to this x equals 2 from the left side, well, the y, it's just getting closer to 4. Even though there's this 6 here, there's not really much in the function that's saying, hey, I want to go to 6. It really looks like it wants to go to 4. So that left-sided limit, that should just be a 4. And if we try the same thing from the right side, so it'll be the right side limit of f of x. Well, same thought process. As we get closer and closer to 2 from the right side here, it still just wants to get closer and closer to 4 despite that 6 being there. So that right-sided limit should also be 4. So again, the way that we find the actual limit of a function is just by comparing these two one-sided limit values that we've already found. And since they're both equal to each other, we know that 1, the limit exists, and 2, the limit is equal to that same value, just like we said before. So the limit should just be 4. And again, if you feel more comfortable graphing this out, you can always take out a sheet of paper and then graph this out to see that this limit still works, as we saw. So let's take a look at this final case with limits with tables. Okay, so as we can see, as x gets bigger, the y also gets bigger. There's a little bit of a weird thing happening here. So at x equals 2, we're at 4, but then as soon as we move a little bit to the right of 2, we're all of a sudden at 5.01. So this function is, it's doing a little bit of some hardcore parkour. And we can pretty easily see as a result of that, there's a jump discontinuity. But despite that continuity, let's try to apply some calculus to this. So let's try the limit as x approaches 2 from the left side of f of x. Well, if you look back at the table, we see that from the left side, as x gets closer and closer to 2, the y is getting closer and closer to 4. And it kind of matches with what the function value actually is. But in this case, it never matters what the function value is. We just want to look at what y is approaching. And it's approaching 4. So that should be 4. And if we try the right-sided limit, so the limit as x approaches 2 from the right side of f of x, while looking at the table, we get closer and closer to 5, not 4, whenever we're looking at it from the right side. We see here we have 5.1, 5.01, and then all of a sudden there is this jump to 4. But remember, with limits, we only care about what the function looks like it's going to do. So this limit right here should just be a 5. And now we can apply the principle we learned from the last episode and apply the regular limit as x approaches 2 of f of x. Well, remember, if we see that the two one-sided limits aren't equal to each other, then the limit value actually doesn't exist. So we say here that this limit does not exist. So that's kind of how jump discontinuities look like on tables and how to apply calculus to them. So there is a quick little nuance I want to point out about tables. So if you look at a table, let's say here between 1.9 and 1.99, we only have the points corresponding to x equals 1.9 and x equals 1.99. For all we know, 1.95, for example, that could be like all the way up at y equals 20. So just always keep in mind, whenever you're working with tables, it's not really guaranteed that what you're observing and the conclusions you're making are what actually happens, but just based on the information you see on the table, it's a safe conclusion to make. That just about wraps everything up. If you want the notes for this video, the link will be down in the description. Thanks for watching. Be sure to check out the preceding lectures and let me know of any suggestions that you may have for this video or even the lecture series in general. Have a great day.